Um, yes, so thanks to the organizers for this amazing initiative and a marvelous conference that I really look forward to. I already enjoyed today, and I look forward to the rest of the day, rest of the conference. I appreciate, well, the conference has some very big motivations, but also the little things like being a vegan and having a vegetarian and vegan table is very nice. I also appreciate that this is the last talk on a day on which many of you might be tired, jet lagged, some sleep deprived, including myself, so I will try not to go beyond time. It's good that we start a bit early. Right, so yes, as the title says, I'm going to talk about a result, which is a quantum advantage for finite clocks. This is work with Misha Woods, who's the lead author, along with myself on this work. Gilles Putz, Sandra Stupar, and Renato Renner, all of whom are or were at ETH Zurich while this work was being done. Right, so to explain, well, first I should really talk about what I consider a quantum clock to be, because clocks, the term clocks is used in quite a broad sense in the community, and we are using it in a very specific way. So what I mean by a clock is a self-contained device that autonomously outputs time information. And there are two important parts here. The first is self-contained, meaning that the clock a clock somehow extracts information about the passage of time and outputs it to the external world. So the only time information must come from the internal dynamics of the clock itself and not from an external source. The second part, the autonomously outputting time information, is important because it differentiates it from what I will discuss to be a stopwatch, which is that the clock is not asked for time information. It keeps a continuous stream of information on its own. So in practice, what this would mean is, imagine that you have a set of events. Your plane landed, somebody had a cup of coffee, the second talk of today, just some collection of events, and you don't know what order that they appear in. Then the goal of a clock essentially is to keep broadcasting ticks to the external world so that every time an event happens, when it happens, you can attach to it a label, which is essentially the number of ticks that the clock has outputted until that time. So you listen to the clock and it doesn't tick for a while, and then every now and then it gives you a tick. And at the end, you are able to classify your events based on the ticks. So if each of the red marks are the ticks, you can say E2 happened in the first interval, E3 and E4 happened in the second interval. You may not have a clock that's good enough to differentiate between all of the events. But essentially what the clock does is it provides you an ordering for events by giving you ticks. And so in this sense, it acts as an independent reference frame for time. It broadcasts its time to the rest of the universe. And what's important to say is what a clock is not, in the sense that we consider it. It's not a stopwatch, and it's not exactly what metrology considers. Sorry. And the reason is because for a stopwatch, a measurement is triggered by an external event. So I can imagine that Usain Bolt is running a race. When he takes off from the starting line, I trigger the state of the clock to be in a certain initial state with some dynamics. And then when he passes through the finish line, I will then measure the state of the clock. So in contrast, I can measure the state of the stopwatch. In contrast, a clock, as we consider it here, is continuous. The measurement is continuous and included in the dynamics. So the clock's own dynamics includes the measurement process. The output for a stopwatch can be any real number. It's a time, whereas the output for a clock is really an integer number of ticks in most basic sense. And so those are the conceptual differences between stopwatches and clocks. Technical difference is that the dynamics of a stopwatch in between the triggering and the measurement is unitary, whereas because a clock must output information to a register via continuous ticks and measurements, it is by definition a bipartite or an open quantum system. And more practically, what this means is that for stopwatches, you choose the measurement to optimize the estimation of the state that you're in so that you can get the most information about time. Whereas for a clock, you need to choose the measurement to both optimize the information about the state, but also not to disturb the dynamics of the clock, because the measurement is really a continuous weak measurement. And in terms of the result that we have, we do get a quantum over classical advantage that is quadratic, as you see. But this is with respect to the dimension of the Hilbert space of the clock, whereas the quantum of classical advantage for stopwatches and for metrology is with respect to other parameters, such as the number of database queries or the number of systems that you process either incoherently or coherently together. Right. So this is the most technical equation that you will see in this talk. And it's the formulation of what a quantum clock does. And essentially there are a few parts of this equation, which is the map from a clock to a clock and a register. And the register very basically is just a bit, which is 0 if it's not ticking, 1 if it ticks. And so then you have a part of the dynamics that is just an arbitrary open quantum system dynamics, a Lindbladian with a Hamiltonian as well as some Lindblad operators that corresponds to nothing happening. So no tick on the register, even though the clock may evolve. And then there's a part that corresponds to a tick being outputted, and this, as you see, is just is an arbitrary measurement. It's a channel, essentially. So this is the most general case of a quantum clock, but because we only want to prove an advantage and we don't really prove the general case of the best quantum clock, we take a simple case. And the simple quantum clock that we consider is, first of all, we focus only on a single tick of the clock. So indeed, you could use this equation to consider a sequence of ticks, and then you can ask whether it's an IID sequence or not, and whether there are correlations in between ticks. But for us, we will just consider a single tick, because this suffices to characterize reset clocks, or IID clocks, which is what already is optimal, at least in the classical case. And in that case, you can replace this entire measurement channel by just an operator, which is the sort of the entire POVM element corresponding to that measurement channel. And we consider the case where the internal dynamics don't have any Lindbladian, so it's just a Hamiltonian. And in this case, it simplifies. You just get a modified version of Schrödinger's equation with the usual Hamiltonian. And V here is now a positive potential because it's a POVM. So this really acts like an absorbing potential. So now you just have Hamiltonian dynamics with an additional potential which absorbs some of the norm of the state corresponding to the probability of a tick being generated. And that's just the expression for the probability per unit time of the tick. So before we talk about the result, I should characterize what I mean by the performance of a clock. So we should talk about two things: the resources and what I mean by accuracy. Our focus in this work was on the Hilbert space dimension of the clock, so just the number of available orthogonal states. You could consider energy as well. This is not the focus of this paper, but it is interesting. One trivial effect of energy is to scale up frequency. If I have any physical system and I just multiply all of the energies involved by a constant factor, then the frequency, everything will just go that much faster, and the frequency will be multiplied by that factor. But that's not very interesting. A more interesting question is to consider thermodynamic autonomy, which is to say that the sources of energy should be incoherent parts, so they cannot have any time information on their own. They are always in equilibrium. And this is a question that we considered in a previous work, published in PRX, which suggests a very fundamental connection between the accuracy of clocks and entropy dissipation, much like the other works in the direction of the arrow of time and thermodynamics. So in any case, for us, D is the resource we consider. And for us, the accuracy will be what we call the regularity. And this is just the ratio between the first moment squared and the variance squared of the probability distribution of the tick of the clock. So if it's a perfect clock and the probability distribution is a delta function, then this ratio is infinity because the variance is 0. But for any other imperfect clock, it's a finite number. And this has a number of advantages. First of all, it's scale invariant. If you take t and you multiply it by a factor, because of the ratio of squares, a vanishes, which means that the frequency of the clock doesn't really appear in this expression, which means this sort of ignores the time scale over which it occurs and only really cares about the regularity of the ticks with respect to each other. And it's also the answer to the following question: how many ticks before the error of the clock is a single tick? So from the watch in my hand, this would be how many seconds before my watch's error is of the order of 1 second, because it ticks every second. You could consider other measures. For example, a more operational measure would be the number of alternate ticks. If you took two such clocks and played them against each other, with the constraint that they would continue to play as long as every tick of one clock was followed and preceded by the tick of the other, and they would lose when one clock would tick twice before the other. This was considered in this paper by Sandra, Yongcheng, and Renato. But it's not just the alternate ticks. To me, it's really the first characterization of a quantum clock really as an independent reference frame for time. So I recommend that work. Right, so with all of this setting in place, the mathematical formulation and what we want to study, let's consider the trivial case, a one-dimensional clock. So here it's not really quantum or classical, it's just one real number, a positive number lambda, which is the probability per unit time of ticking. And what this means is that the probability per unit time of ticking is really independent of time, in the sense that given that the clock is not ticked before then, it's really not going, the probability doesn't change in time. And what you end up with is essentially a decay function. This is what I would call the delay function of a Poissonian clock. And you can calculate the moments of this clock, the first, second moments of variance, and it's quite trivial. What you end up with is a regularity of 1. So somehow to say that in 1 tick of this clock, your error is already of the order of 1 tick. So it's the most trivial clock. There is one way that you can improve regularity quite trivially, which is by post-processing ticks. So this is to say that rather, if I have a clock that keeps outputting ticks, rather than output each of these to the external world, I just wait, I count n of these ticks, and then I output 1 to the external world. And this is somehow a trivial signal-to-noise manipulation, because the signal goes as n, noise goes as square root of n. And so what you end up with is that the delay function is just the n-fold convolution of the original one, and so the regularity becomes n times the regularity of the original one. So with a Poissonian clock, if I bunch together n ticks, I would get a regularity of n. And what's interesting, and this is one half of the major result of our paper, is that the optimal classical clocks are no better than post-processing. And so what do we mean? So a classical clock is the same as when I consider the quantum clock, but we restrict the dynamics to diagonal states in fixed bases. So the initial state is diagonal in a particular basis, and the dynamics always keeps it diagonal in that same basis. This essentially means that the Hamiltonian part is 0, and you just have some Limbladian, well-chosen Limbladian operators. And so you end up with stochastic dynamics on population vectors. You can describe the state as d positive real numbers. The rate of change of the state is just some Kolmogorov generator times the state. And the delay function is some positive matrix times the state. And all of these are just d times d matrices. And the best clock in this case, so we optimized over all possible versions of n and t. And the best clock turns out to be a simple ladder clock, which is where you start the clock in one of the states. The dynamics of the clock essentially corresponds to moving from one state to the next. And so there's a single off diagonal in this matrix. And finally, the tick is generated from jumping from the last state back to the first. And so this really is, again, counting ticks. You're using each of the steps in the ladder as a mini tick, and you're only outputting it after d of them. And so from the argument on the previous slide, you get that the delay function is the d-fold convolution, and so the regularity becomes just d. And so now the question is, can quantum clocks do better? And before going into mathematical details, let me give you a bit of intuition as to why we could expect quantum dynamics to do better. I might be going quite fast. Yes. So in the classical case, incoherent dynamics is mathematically essentially a biased random walk. So you have a property of moving forward, a property of staying in the same place, a property of moving backward in all of this dynamics. So when you essentially look at the time evolution of the state, what you see is that the mean, even though it moves as t, there's always going to be a spread which is proportional to square root of t. And there's a minimum amount of the spread that you cannot get out of. And so this leads to the signal to noise ratio t by square root of t, which is really the same as that what you would get from bunching n ticks of a clock, which is exactly why you get the result that even if you have a classical clock of dimension d, you could use its dynamics, or you could just use it as a memory to count ticks, and it gives you the same improvement in the regularity. But quantum dynamics has a possibility of not spreading the same way. And I say has a possibility because it's not exactly that it doesn't spread. But imagine now, let's do the thought experiment. Consider that you had d states, and you had the case that you were able to evolve continuously within this d-dimensional space without spreading at all. So you have these states, and the clock goes from psi 1 to psi 2 to psi 3, all the way to psi d, and then it ticks from the last one to the first. Then again, your mean will go as the number of states, but your uncertainty here will be of the order of 1. Now, it's important to see that the uncertainty cannot be 0, because the evolution is continuous, which means that you cannot jump from one state to the next. There is an uncertainty you have to rotate somehow from each psi to the next psi, so you will always have an uncertainty of order 1 in when you arrive at a state from which you're going to tick. But if you could get this, that the uncertainty was of the order of 1, then you could expect that the regularity was of the order of d squared. And this is really the quadratic advantage that we're looking for. And now the question is this possible with d-dimensional quantum states? And here I would introduce what we call the quasi-ideal clock, which is a special clock that somehow shows that it's one class of clocks that shows that this is definitely possible. And it's based on a paper with Misha and Jonathan Oppenheim that is actually was on the archive quite a long time, but it was recently, last month, published in a French mathematical journal. And what it does is the following. So the Hamiltonian of this clock is a d-dimensional Hamiltonian that is just an equally spaced energy ladder. So it's kind of like a harmonic oscillator that you truncate, equally spaced energy levels. And this was introduced by Saliker and Wigner in the 1950s. And it has a property that you can write down another basis of states, mutually unbiased with respect to the energy eigenstates, that you can call angle states somehow, or time states. They are equal superpositions of all of the energy eigenstates, and they have the nice property that if you start in one of them, then at discrete intervals of time, you would evolve to the next one and to the next one and so on. So if you start at theta 1, you know you will, in some period of time, go to theta 2, to theta 3, all the way back, to theta 12 in this case, because the dimension is 12, and then back to theta 1. So it really is the finite dimensional quantum mechanical version of the clock that's on a wall somehow. The problem with this clock, or at least these states for the clock, is that they fluctuate. At those discrete intervals of time, you can expect them to be precisely at theta 1 and theta 2, but in between, they are going to be superpositions of many different angle states. And in fact, on average, they will be superpositions of a square root of d angle states. So where d is a dimension. However, we know that square root of d was exactly the uncertainty that gave us the classical signal to noise ratio and then the regularity of d. So clearly, if we use these states, then the average noise is going to be of square root of d, which means that we're not going to get a better than classical result. So this is not the state we're looking for. And the main result of this work with Misha and Jonathan was to say that instead of starting with a delta function in terms of the angle states, you could start with a Gaussian instead. So you allow yourself an initial width. And what that does is that because you have that initial width, you now are not precise at these discrete intervals of times, but you trade off that imprecision in your initial state towards increased stability. So you will not fluctuate as much as time goes by. And so now we consider more specifically how well we can do this. So for example, back to the thought experiment before. If we could manage to make the uncertainty to be of the order of d to the eta, where, so for example, for classical clocks, eta would be half, because you get square root of d, then because the mean is still d and the uncertainty is d to the eta, then r would scale as d to the 2 minus 2 eta, because mu squared by sigma squared. So our question is, how small can eta be? So for the Perez state, you start with an eta which ostensibly is 0, but then it fluctuates, so you end up with square root of dimension. So you have to start with an eta that's not 0. But if you start with too large of an eta, then you've lost already, because you have a width that's too large. And you can see this in this diagram. So these three cases are different initial sigmas. So the orange case is where you start with an energy eigenstate that is a superposition of all of the possible angle states. So it has a rather large uncertainty, and it just stays there forever. The interesting one is the blue one, which shows that you can reduce the uncertainty and have it be quite stable. And this is for, if I recall, dimension 8 or maybe 10. So it's still quite a low dimension, and it's quite stable. And then you can see if you try to push this even further to the green one, where you start, well, the green one is essentially the Perez states. So you start with sigma being 0, but then it fluctuates massively, and so on average it's still quite large. And so the answer to the question, how low can you push this blue curve down and still stay quite stable, is in fact, well, this is I would say the other half of the result. Via a great deal of function analysis, you can prove that eta can be made as small as you like in the asymptotic regime of large dimension. So as the dimension goes up, you can in fact make this width as small as you like. And to be more precise, you can prove that for every epsilon greater than 0, you can find a family of clocks with increasing dimension, these quasi-ideal clocks, such that the regularity is greater than d to the 2 minus epsilon, which essentially means that you can get as close to a quadratic advantage as you like. Right, so let me tell you some representative results. So for instance, for d is equal to 2, which is qubit clocks, you can get r is equal to 4, which is d squared in this case. This is the only case where you get such a nice result. It's also the only case in which it's analytically tractable. And the clock is rather simple. You start with a Hamiltonian in the z direction, which induces a precession around the equator. Your initial state is on the equator, so you could start with the plus state. the X eigenstate. And your potential that generates ticks is really a projector on the opposite eigenstate minus. So you can intuitively think of this as a clock that starts there, rotates about the equator, and as it passes through this potential, it ticks. And you get R exactly equals to 4. For slightly higher dimension, you do see what we predicted. So the orange line is the classical bound. R is exactly D. The blue dots are the Perez states, and they are better. So for D is equal to 2, the Perez state and the Gaussian states are exactly the same because they're only 2 eigenstates. But as dimension increases, it really doesn't give you better than a linear scaling, so it's not really improving much better than the classical bound. But the quasi-ideal clock do demonstrate, these do demonstrate a superlinear scaling that in fact with some more recent numerics you can see for much larger values of the dimension. I have here 10, 20, 50, and 100 and the corresponding regularities. And there are two ways of looking at the regularities. You can say, imagine that R was a power of the dimension. What is this power? And you see that as D increases, it's getting closer to 2, from 1.6, 1.7, 1.9. And the other way of looking at it is to say, let R be a constant factor times D squared. So you say, oh, I think it's quadratic. What is this constant? And that constant is also improving and getting closer to 1. So it's as somehow as we expect. And yeah, out of interest, for D is equal to 100, the clock that generates this result is the width of the clock the width of the Gaussian state as well as the width of the potential on the other side of the space is about 2.94. So remember, square root of D in this case would be 10. So that would be like essentially as good as a classical clock. So this one is thinner, but it's not a delta function, so it's not of order 1. And in fact, it's like D to the 0.23, which makes this result quite good because by the thought experiment earlier, we could expect something like 2 minus twice of this power, so 1.5, but in fact we get 1.9. So in fact, the thought experiment was almost a worst case scenario. And so that really concludes the results of this work. So in summary, the main result is that if you have a quantum and classical clock, both of size D and that are outputting ticks, the regularity of the classical clock is always less than D. The regularity of the quantum clock can be made to scale as close to quadratic in D as you like. And there are a number of open questions from this that we are working on. One question, which is quite foundational, is about the information that a clock outputs. So somehow the regularity R, the number of alternate ticks, they are all sort of facets that signify that at a very basic level, what a clock does is extract information about the passage of time and outputs this. So if there is a measure of such information, then it would somehow unify all of these different ways of looking at the accuracy and synchronization of clocks. Another question is the trade-off between the clock dynamics and disturbance. So as I said before, this is quite distinct to a single-shot information disturbance trade-off because it's not just what's the best amount of information versus disturbance you can get on one application of the measurement, but rather if you have a measurement that's acting continuously, that's part of the dynamics, what is the best information you can get versus the disturbance that you sort of encode for future measurements. And the third question is to connect clocks in a network. So rather than consider them completely self-contained, consider that they can actually receive and output time information. And well, I won't go into this because Praveen will present a very nice result on Thursday in this direction. Yes, and with that, I would like to conclude and say that if you'd like to know more, you can read these works. This is the archive link to the work that I talk about. This is the archive link to the thermodynamically autonomous clocks. This is for the introduction of quasi-ideal clocks, and also the paper by Sandra, Yongcheng, and Renato, which really made a framework for quantum clocks as reference frames, independent reference frames, is in this link. So yeah, you could also just come and talk to me. I'm very happy to discuss all of it. Thank you.
Thank you, Ralph. Any questions? Maybe I have a question. So that last thing you said about linking clocks together, that reminded me that relativity is a thing. And I was wondering whether there's any connection, like, can we infer anything about relativity? Because it seems like at the core of relativity is autonomously time outputting things. And this is a good example of it. And I haven't quite made any link in my head, but maybe there is one. I
would say that from this work, there is not a direct link, but indeed the somehow the purpose of this work, and in fact the first work that Renato's group did was in this direction. They wanted to consider, because in relativity one of the ways of formulating space-time without just space and time in the background is to say there's just a bunch of clocks that keep emitting their proper times, and then you write down the proper times, give you the reference frame. So this is really in that direction, and I would say that somehow the first question is in that direction. How much information does a clock output? Because then we would be able to somehow say, if you have a network of clocks and they all output information, how much, like how do you link the emergence of a background space-time with this with the amount of information?
Okay.
So yeah, it's a very good question. It's one that we're sort of thinking about, but it's not directly in this work, but yeah, it's
sure.
Motivated by it. Yeah.
Cool.
This is more like a comment and also mostly a follow-up to your question, which is I'm aware that there are people who are working on like quantum clocks and sort of trying to recapture the Wheeler-DeWitt equation using a quantum notion of time instead of a classical notion of time, and so essentially having this like universal wave function being a stationary thing through which you pick out a path in space-time instead. And so you might be able to comment more on how that relates to what you're doing here with your notion of time.
Sure. If I understand correctly, so is this related also to Page-Wooter's formalism of writing down a state of the universe and then saying that one of the subsystems is sort of the clock parameter degree of freedom, and then you rather than there being the time is emergent as one of the degrees of freedoms of a subsystem. Yes, so this is also not directly related to this work, but it is follow-up work that we're doing. And in fact, we have partial results to suggest that one can do this somehow with, so somehow I look at the Page-Wooter's formalism as one extreme, where you start by defining a perfect clock that you can use to give you parameter time. But in fact, what we can show is that you can consider any system, break it down arbitrarily, break down the Hilbert space arbitrarily into subsystems, and with that you can always define the dynamics of one with respect to the other. And it really uses the mathematics that's in this. It's again not part of this work, but it's in that direction. It shows that one can always have time be emergent. It won't be perfect depending on the dynamics of and the size of Hilbert space, but one can always construct such dynamics. We'll be happy to discuss this.
Interesting. Thank you for the insight.
Cool.
Hi, Ralph. Thanks. So at the beginning, when you kind of switched from the classical to the quantum setting, you started with this thought experiment, and you said, well, I mean, in theory, this means that we could get up to d squared. So is this possible, and so on. But was this also an argument as to, I mean, was it clear at this point, or should it have been clear to me that it's impossible to get better than d squared?
I strongly think that this is the same argument goes both ways, that you cannot get better than d squared because the fact that you need to rotate from one state to another quantum mechanically means that there is this minimum uncertainty that you cannot get out of. But we haven't proven that yet, because in the general case to prove it is, well, at least we haven't found a way. But my intuition is that the same argument says we cannot get above d squared, yes.
No, I was just wondering whether there's a formal proof of this.
Yeah, no, there's no. Well, if that was there, then it would have been in this work, but we didn't manage to get one.
Cool, thanks.
Any more questions? Otherwise, let's thank Ralph and all the speakers today again.